This is lecture 6, part 2 for artificial starting solution. In our previous video lecture, we cover one method for finding an artificial starting solution before implementing the simplex algorithm. That method was called the M method. In this lecture, we're going to cover a second method that is also useful to find an initial solution for a linear program. That initial solution is based on the use of artificial variables. And as we did for the M method, in this method, we are going to find the initial solution, and we're going to take out those artificial variables before we implement the simplex method to find the optimal solution for our LP problems. So let's discuss the two-phase method. Again, this is a second strategy. The first strategy was the M method. The second strategy is the two-phase method to find an initial solution to linear programs when you don't have access to slack variables to find that initial solution. So the two-phase method eliminates the use of the constant M as presented in the previous video lecture. In the M method, we use this constant M, which is a very large value that is used to penalize the artificial variables in the objective function. So in this method, we don't use those constants. The two-phase method eliminates the use of the constant M. The method solves the linear program in two phases, and that's where the name comes from. In phase one attempts to find a starting basic feasible solution. And if that is achieved in the first phase, then phase two is invoked to solve the original problem. So in this, at the bottom of this slide, we have a summary of the two-phase method. So in phase one, we put the problem into equation form. So those inequalities has to be changed to equations using slacks or excess variables. So we put the problem into standard form. And we also add the necessary artificial variables to the constraints, just like we did for the M method, to secure a starting basic solution. Next, find a basic solution of the resulting equations that always minimizes the sum of the artificial variables. And this is very important because we are going to formulate a new LP problem in the first phase, which objective function will be the minimization of the sums. So as stated here, minimizes the sum of the artificial variables. And that is regardless of whether the LP is maximization or minimization. If the minimum value of the sum is positive, the LP problem has no feasible solution. Otherwise, if that's not the case, we proceed to phase two. And in phase two, we use the feasible solution from phase one as a starting basic feasible solution for the original problem. So let's work with an example. So in here we have example number 2, which is a minimization problem for x1 plus x2, subject to 3 constraints. The first constraint is an inequality. The second constraint is a greater or equal to inequality. And the third constraint is a less than or equal constraint. So using a E1 as a surplus in the second constraint and S1 as a slack in the third constraint, the equation form of the problem is given as here. So now we have an excess or surplus variable, which is subtracted from 4x1 plus 3x2, and we have the slack variable for the third constraint, which was a inequality. So greater or equal to, we subtract an excess variable. less than or equal, we add the slacks. So we have the problem in two standard form. In phase one, the attempt is to find a starting basic feasible solution for the original problem. And as stated earlier, we replace the original objective function z, regardless of whether the problem or the original problem is minimizing or maximizing, with a new objective function which is going to minimize r. R equals the sum of the artificial variables. And solving this new minimization problem, this is how our objective function is going to look like. So we want to minimize the summation of the artificial variables. Again, it's a new objective function for phase one of the two-phase method. In the first phase, we are trying to find an initial solution for our problem using artificial variables. But the goal at the end is to, after finding that initial solution, that we don't have, we have artificial variables that has a value of 0. And we achieve that by using these new objective function. So our original problem is now looks like this for phase one. So as mentioned earlier, we have a new objective function for phase one. And we have two artificial variables because we need an artificial variable for the equality, and we need a artificial variable for that constraint that has an excess or surplus variable. For this constraint number 3, we don't need an artificial variable because we already have the slack variable that can be used as part of the initial solution. So we only add two artificial variables, one for the constraint that was originally an equality, and the second is for that constraint that has an excess variable, because we need the artificial variables to set up that initial solution. And since we have two artificial variables, then our objective function for the first phase is the summation of those two artificial variables. If, for example, in another problem, we had 3 artificial variables, then the objective function will be the summation of those 3 artificial variables. If, for example, in another problem, we only have 1 artificial variable, then the objective function for phase 1 will be equal to the minimization of just that artificial variable. So in this case, we have 2 because we have 2 artificial variables in the constraints. So using the artificial variables and the slack variable, we can find a starting basic solution for our problem, which is going to be R1, R2, S1 equals 3, 6, and 4. So this is, again, our, this is the same formulation that we had in the previous slide. The reason I'm showing it again is because we need to set up the associated tableau. So I'm showing the formulation and then the tableau at the bottom. So as we did for the simplex method, so now we are going to apply the simplex method to phase 1 of the two-phase method. So in row 0, we have the negative values for the artificial variables, R1 and R2. And then for each constraint, we have a row. So for row 1, we have these coefficients in which the original or the artificial variable is part of the identity matrix, which is part of the basic variables for this row. Same thing for R2 and for S1. So that's our initial tableau. Before proceeding with the simplex method for phase 1, the R row, which is that row 0, let's call it 0, 1, 2, 3, that row 0, the R row must be made consistent with the rest of the tableau, as we did for the simplex method. So R1 and R2 are substituted out in the R row by using the following operation. The new R row is going to be equal to the old R row plus 1 times R minus R1 times minus rho plus 1 times R2 rho. So basically what we are doing is we want to make this 0 and this equal to 0, so the tableau is consistent with the initial solution. And we do that by performing the elementary row operations. So the first one, we multiply row 1 times this row, and then we add it to row 0. And for the second one, we multiply this row to row 1 times 1 and row 2 times 1 plus row 0. So the new tableau, after performing those operations, had these coefficients in row 0. Now these are the new coefficients, and as you can see, these two coefficients are now 0, and this value for the objective function went from 0 to 9. And this is correct because if you remember, the objective function for the phase 1 is minimization of R, which equals R1 plus R2. And in this problem, R1, or in this tableau, R1 equals 3, R2 equals 6. So 3 plus 6 equals 9. So this 9 is the value that we observe here. In addition to that, we have that identity matrix now in the right format with zeros and 1. So this is consistent. Question now is, for this first tableau, do we have an optimal solution? So we are doing a minimization problem. And we know that for minimization, in order to see whether or not we have an optimal solution, we need to look at that first row, or row 0. And if we have a positive value, then we know that we haven't found an optimal solution. So in this case, we have two positive values. The largest is x1, so we can decide to enter x1. And then we had to perform the minimum ratio test to decide who's going to leave. So for this case, we have 3 over 3, which is equal to 1. We have 6 divided by 4, and we have 4 divided by 1. So the smallest will be equal to 1. So that means that R1 is leaving the solution, which is what we observe in this first table. X1 in yellow is entering, R1 is leaving in green. So R1 is now substituted by X1, and we need to make X1 as we did for the simplex method. So we have to change this using the elementary row operations to this format. So this tableau is showing the resulting values after applying the elementary row operations. So we went from here to here. So at this point, we also find whether or not we have an optimal solution. So we go to row 0 again, and we find that there's a positive value here, which means that X2 can enter the solution. And we perform the minimum ratio test. And the minimum is 1.2, which tells us that R2 is leaving the solution. So when you move from here to here, you'll see that R2 is no longer part of the basics because it's substituted out by X2. And we have to transform this column in, so originally this was the value, so we need to make this column now zeros and ones using the elementary row operations. So again, this is the result after applying the elementary row operations. And at this point, we can see that there's no positive, other than zeros, positive coefficients in row 0, which means that we have an optimal solution. Also, we were able to take out the artificial variables from the basics. So the artificial variables are no longer part of the basics, which make them equal to 0, which is what we wanted for phase 1. We don't want an artificial variable to remain a basic variable with a value different than 0, because that means that the artificial variable is part of the solution. So we don't want to see that. What we want to see is what we are observing here. So there's no artificial variables in the basic variables, which make this right-hand side of the objective function value equal to 0. So the new R row is used to solve phase 1 of the problem, which yields the following optimal tableau, which is the same tableau from the previous slide. Because the minimum R is equal to 0, phase 1 produces the basic feasible solution. X1 equals 3 over 5, X2 equals 6 over 5, and S1 equals 1. At this point, the artificial variables have completed their mission, and we can eliminate their columns altogether from the tableau and move on to phase 2. Okay, so we can take these 2 columns out of the problem now, because they are no longer needed. We found our initial solution. And this is how the problem, now we substitute the original objective function back to the problem in phase 2. And these coefficients are based on these coefficients here of the solution or phase 1. So those and those coefficients are the ones that we are observing in this part of the constraints now. Phase 1 has transformed the original constraints equations in a manner that provides a starting basic feasible solution. The tableau associated with phase 2 problem is thus given as this. So these are the coefficients from this problem, right? So now the coefficients of the objective function are listed. And our basic variables are coming from here. So X1, X2, and S1. But the same problem, if you look at those basic variables, these 2 constant values are not equal to 0. So that's, we need to fix that. So again, because the basic variables X1 and X2 have non-zero coefficients in 0, they must be substituted out using the following operations. So again, we are gonna multiply this row, let me call this, so these are the basics. X1, X2, S1, and this is row 0, 1, 2, and 3. So we multiply row 1 times 4, and then we add that to row 0. And we multiply row 2 times 1, and we add that to row 0. So the goal is to make these 2 equal to 0. So after performing those operations, the initial tableau of phase 2 is this one. So again, our basics are X1, X2, and S1. And you can see that now those columns are 0s and 1s. So those are our basic variables for our initial solution. Because we are minimizing, E1 must enter the solution, right? Because this is a positive value, and this is a minimization problem. Application of the simplex method. So now at this point, we have the problem, we have the initial solution, and we can apply the simplex method as we know it. So application of the simplex method, we produce the optimum in one iteration. So if you apply the simplex method now, you will find the initial solution after substituting this E1 into the basic variables. The removal of the artificial variables and their columns at the end of phase one can take place only when they are all non-basic, which is what we observe in the example. If one or more artificial variables are basic at 0 level, then the removal requires the following additional steps. So step 1 selects a 0 artificial variable to leave the basic solution and designate its row as a pivot row. The entering variable can be any non-basic and non-artificial variable with a non-zero coefficient in the pivot row. Perform the associated simplex iteration. Step 2, remove the column of the just leaving artificial variable from the tableau. If all the 0 artificial variables have been removed, go to phase 2, otherwise go back to step 1. Okay, so that concludes this lecture on artificial starting solutions, in which we focus on this second method, which is called the two-phase method, to find an initial solution for LP problems that do not have an initial solution given by slacks or slack variables. So when those slacks are not available to provide an initial solution, we have two strategies to find an initial solution. The first strategy is the M method, or the second strategy, which is the one discussed in this video, which is called the two-phase method.